Okay, so let's talk about our second speaker from Kyoto, Akihiro Kanemitsu. So you can talk on your Fano manifolds and stability of tangent bundles. Where you are.
Thank you very much. Thank you very much for the introduction. And also, I'd like to thank the organizers for giving me this opportunity to talk here. And today, I'd like to talk about Fano manifolds and the stability of tangent bundles. And okay, and this is a plan for my talk. In the first section, I will present an introduction about stability of tangent bundles. Then in the next section, I will use the main result of this talk. And in the third section, I will explain the main result by introducing one example, the case of B434, which I will later explain. And then finally, I'm going to give some remarks about the problem and the main result. So, okay, now let me start with an introduction. And in this talk, our Fano variety X is a smooth projective variety with anti-canonical divisor minus kx. And from the viewpoint of birational geometry, we expect that we can decompose varieties into three types of varieties according to the positivity or negativity of canonical divisors. And the Fano varieties form a class of such building blocks. And today I'd like to study the stability of tangent bundles for Fano manifolds. And so in the next slide, in this slide, let me briefly recall the definition of stability of vector bundles. So let X be a smooth projective variety of dimension n, and Hx be an ample divisor on X. And suppose that we are given a vector bundle E, or more generally, a torsion-free sheaf on X. Okay, then the slope of E is defined as the average degree of the first Chern class of E. So the slope mu of E is the quotient of the degree of the first Chern class of E by the rank of E. Okay, then this bundle E is called semi-stable if this condition holds. So for every subsheaf F of E, the slope of F is less than or equal to the slope of E. And this bundle E is called unstable if it is not semi-stable. And in this case, a subsheaf which violates this inequality is called the stabilizing subsheaf of E. And similarly, a stronger notion, stability, not semi-stability, but stability, is also defined by replacing this inequality by a strict one. But today I will concentrate on just semi-stability for simplicity. Okay, so now we have defined the notion semi-stability for a vector bundle. Then one can ask when the tangent bundle is semi-stable. This is a very, very natural question, and there are some answers to this question. For example, if the canonical bundle is ample, then the tangent bundle Tx is semi-stable with respect to the canonical polarization. And also, if the canonical bundle is trivial, then the tangent bundle is also semi-stable. And in this case, with respect to any polarization. And this follow from the existence of Kähler-Einstein metrics on these varieties, which is proved by Calabi and Yao. Okay, so roughly speaking, if the canonical bundle is semi-positive, then the tangent bundle is semi-stable. But if the canonical bundle is negative, equivalently, if X is a Fano variety, then the situation is different, contrary to these phenomena. In general, the tangent bundle of a Fano variety is not semi-stable. So for example, let X be the projectivization of O1 and O on P2 and consider the natural projection. Okay, then the relative tangent bundle of this projection gives a subsheaf of Tx, and its slope is 20, which is greater than the slope of the tangent bundle, which is 56/3. So the relative tangent bundle gives a destabilizing subsheaf of the tangent bundle. So the tangent bundle is not semi-stable in this case. Okay, and this is the last example. And in this example, the stabilizing subsheaf is given by a relative tangent bundle of a contraction pi. And it was believed that this is a general consequence of the following conjecture, which is due to Peternel and Stephens. This says that, so let X be a Fano manifold and assume that the tangent bundle is unstable. Then there exists a contraction phi of X whose relative tangent sheaf gives a stabilizing subsheaf. Let me give one comment. Precisely speaking, Stephens didn't state this as a conjecture, but he studied this in dimension 3 and gave an affirmative answer. Then later, Peternel stated this as a conjecture in his paper. And actually, this conjecture of Peternel and Stephens is a sophisticated version of the following more naive folklore conjecture, which says that let X be a Fano manifold with Picard rank 1, then the tangent bundle is semi-stable or even more stable. Okay, so we have two conjectures. The first conjecture, which is due to Peternel and Stephens, and this conjecture for Picard rank 1 case. And I will denote this conjecture by conjecture A. And let me give one remark. So the first conjecture implies the second conjecture because there are no non-trivial contraction on a Fano variety with Picard rank 1. So the conclusion of the first conjecture does not hold for any Fano variety with Picard rank 1. So it is just so that tangent bundle is semi-stable. In fact, the first conjecture for the case where the Picard rank is bigger than 1 is enough to conclude the second conjecture. And this follows by considering the product of two copies of Fano variety. Anyway, we have two conjectures, and the main object of this talk is this conjecture A. Sorry, this conjecture A. And let me recall not all, but some known results of this conjecture. So let X be a Fano manifold with Picard rank 1. Then the Picard group is generated by an ample divisor HX. And okay, then the anti-canonical divisor can be written as a product of HX and a positive integer Rx, which is called the index of the variety, this Fano variety. Okay, then with this definition, first in lower dimensional cases, in dimension at most 6, this conjecture A is known to be true. And this is due to Petar-Nerushinsky and Huang. And second, without any condition on dimensions, but some conditions on the index, the conjecture is known to be true. For example, if the index is 1, then the tangent bundle is semi-stable. And this is proved by Reed. And also, if the index is sufficiently large, then the tangent bundle is semi-stable. And these are proved by Petar-Nerushinsky, Huang, and Mock. And let me give one comment on why this conjecture is important. Actually, the conjecture is important for some applications. For example, the conjecture implies a Bogomolov inequality for the manifold in question. And this inequality has some geometric consequences. For example, Reed and Leskowski observed that this inequality implies the bound of Fano's threefolds. And also there are many related results for which I will omit for today, but this conjecture is important for the application to the geometry of Fano manifolds. Okay, now let me go to the main object of this talk. And today I'd like to study this conjecture for Fano manifold with Picard rank 1 for a certain class of Fano varieties which are classified by Pasquier. So let me briefly summarize his classification. So in 29, Pasquier studied holospherical varieties. And as an application of his study, he classified a class of 2 orbits varieties. More precisely, he classified Fano varieties with these conditions. And here, X is a smooth Fano variety with Picard rank 1. And we assume that the identity component of the automorphism group, which I will denote by G, acts on X with 2 orbits. I will denote by X0 the open orbit and by Z the closed orbit. And furthermore, we assume that the blow-up of X along Z is again a 2 orbits variety with respect to this group G. So the blow up the composite into X0 and the exceptional divisor E. Okay, Pasquier classified Fano varieties with these conditions, and his result can be summarized as follows. So there are 7 types of varieties with these 3 conditions. And they are determined by the following triples, these triples. Here are triple D, I, J, consists of a Dinkin diagram D and 2 elements I and J of the free abelian group generated by the nodes of D. And actually this group is isomorphic to the weight lattice of D. So each of I and J can be considered as a weight. Okay, then the 7 triples are as follows. The first one is Bn n minus 1 n, and Bn is labeled as this one, this diagram. And the second case is B3, 1, 3. And the third case is Cn, k, k minus 1. And Cn is labeled as this. And the fourth case is F4, 2, 3. And F4 is this one. And the fifth case is G2, 1, 2. And G2 is this one. And actually, the first 5 cases are more closely related to each other. In the first 5 cases, varieties are holospherical varieties. I will omit the definition of holospherical varieties since the definition is not important for this talk. But anyway, the first 5 cases are constructed similarly and they are related species. And there are 2 exceptional cases. The case P1, and in this case, the triple is F4, 1, 3. And the case P2 is the triple A1 times G2, 1, 0 plus 2. Here, A1 times G2 is labeled as this way. Okay, so there are 7 types of varieties. But the construction of these varieties are a little cumbersome, so I won't explain all examples. But later I will choose one example, the 4, 3, 4. The first case with n is equal to 4 to explain the geometry of these varieties. And this choice, B434, is because this case is very interesting in view of the main theorem. And so now let me introduce the main theorem of this talk. So let X be a Fano variety as above. So one of these Fano varieties. And first assume that the case H1 occurs and it is bigger than or equal to 4, then the tangent bundle is not semi-stable. And second, assume that the case H4 happens, then the tangent bundle is also not semi-stable. And finally, in the remaining cases, the tangent bundles are semi-stable. And in fact, they are stable. So in particular, the conjecture A is not true in general. Okay, now let me give one remark. In his paper, Pasquier determines the group G, the identity component of the automorphism group. And he proved that in the first 5 cases, for type H varieties, first 5 cases, the group G is not reductive. In particular, there are no Keller-Einstein metrics on type H varieties. On the other hand, as is well known, the existence of such a metric implies the semi-stability of the tangent bundle. So these 5 examples are, in a sense, natural candidates for counterexamples. And in some cases, actually, they give counterexamples to the conjecture A. So this is the main theorem of this talk. And okay, in the remaining minutes, I'd like to explain the proof by choosing one example, the case B434, the case H1 with n is equal to 4. But before going into this particular example, let me briefly explain the general strategy of the proof. Okay, so assume that the tangent bundle is not semi-stable, unstable, then there exists a unique maximal destabilizing subsheaf F of Tx. And since it is maximal, the sheaf F is G invariant, and also it is semi-stable. And also the slope is positive, since the slope of the tangent bundle is positive. So then these conditions imply that F defines a foliation on X. Namely, so F is saturated as a subsheaf of Tx, and F is closed under the Lie bracket. Okay, now fix a general point X in X. Then by the Frobenius theorem on integrability, we have the leaf Lx through this point X. And what is this? This is a holomorphic immersion from a complex manifold Lx, such that the tangent bundle T of Lx coincides F in the tangent bundle of X. And this Lx is maximal with respect with this condition. Okay, then theorem of Bogomolov-Makilen or Bost tells us that the leaf Lx is algebraic. So the dimension of the Zariski closure of Lx in X is the dimension of Lx. Also, Lx we have as well with the action of G, since F is G invariant. So if G is an automorphism, then the G image of a leaf closure is a leaf closure of Gx. Okay, by summarizing this, we have this lemma. So if the tangent bundle is not semi-stable, if and only if there exists a G invariant algebraically integrable foliation F, whose slope is larger than the slope of Tx. Okay, now consider the quotient morphism of this foliation, which sends a general point of X to the point Lx bar, the risky closure of the leaf, which defines a point in the Chow variety of X. Then this defines a rational map, which is G equivariant. And so it is resolved after blowing up smooth G centers by the G equivariant Hironaka resolution of indeterminacy. But by the assumption of X, this map is actually resolved after blowing up the closed orbit. So we need to study the blow up of X along Z. And in each case, we can show that the blow up admits a smooth vibration, which I will denote by pi. So the foliation F comes from the relative tangent bundle of pi. So the foliation is the push forward of this, the relative tangent bundle of this smooth vibration. Okay, then the main theorem follows by studying the explicit geometry of the blow up, and this is a general strategy of the proof. Okay, so now let me explain this strategy closely by choosing one example, the case B4, 3, 4. Okay, let C9Q be an orthogonal vector space. And let E be the orthogonal flag variety OFL 3 for C9, which parameterizes flags of isotropic subspaces of dimension 3 and 4. Then this variety, this orthogonal flag variety, admits two natural fibrations, Py and Pz, to the orthogonal Grassmannians, which are denoted by Y and Z, respectively. And here, this map Py maps our flag V3, V4 to the point corresponding to V3. And this map Pz maps this flag to the point corresponding to V4. Then the dimensions are as these. So the dimension of E is 13, and the dimension of Y is 12, and the dimension of Z is 10. And now let me describe the fibers of Py and Pz. So the Py fiber of our point V3 is a set of isotropic subspaces in this orthogonal vector space. The quotient of the orthogonal complement of V3 divided by V3. And this orthogonal vector space is three-dimensional. So this fiber is isomorphic to a conic in P2, which is a projective line. So this Py is a P1 bundle. On the other hand, the Pz fiber of our point V4 is a set of three-dimensional subspaces in V4. And of course, this is isomorphic to P3. So this Pz is a P3 bundle. So this E admits two natural projections, and one is a P1 bundle, and the other is a P3 bundle. And okay, let EY be the bundle on Y corresponding to this P1 bundle, PY. More precisely, EY is the direct image of the pullback of OHZ, the ample generator of the Picard group of Z. The Picard group of Z is isomorphic to the group of integers. And we'll choose the ample generator and consider the pullback of HZ and consider the pullback, push forward of the line bundle. Then this vector bundle E is a rank 2 vector bundle, and E is obtained as a projectivization of this vector bundle EY. Okay, so we have this diagram, and this PY is a P1 bundle, and we defined EY as a bundle corresponding to this P1 bundle. Okay, now we can construct our variety X. So let's consider the projectivization X tilde of the direct sum of EY and O1. Then this variety X tilde contains E as a projective subbundle corresponding to the direct sum and the EY. So here our variety X tilde. And this contains E as a subbundle corresponding to this direct summand. But this E admits another projective bundle structure over Z, PZ. And by considering the normal bundle of E in X tilde, we can show that there exists a blowdown of X tilde along this projective bundle. So there exists a smooth variety X, which contains Z as a closed subvariety. And the blow up of X along Z is this X tilde. Okay, then this image X is our variety X for the triple B434. And actually the first 5 cases for type H varieties, constructions are similar. And okay, so we have this diagram, and our variety X contains Z as a closed subvariety, and the blow up of X along Z admits a projective bundle structure pi. Okay, I will denote by F the image of the relative tangent bundle of pi to X. Then this F defines a foliation on X whose leaves are the images of pi fibers, this P2, this P2. Okay, so we have this diagram. Here, X is our variety, which contains Z as a closed subvariety, and the blow up of X along Z admits a projective bundle structure on Y. And X admits a foliation that is induced from this projection pi. Okay, then we have these formulas. The rank of F is the rank of EY, and the first Chern class of F is the rank of EY minus the first Chern class of EY. And the remainder of X is the remainder of Y plus the rank of EY. And the first term class of x is 2 times dimension of v minus dimension of y minus dimension of z plus 2. And this proposition holds true for the case of type H varieties. They admit similar descriptions, and this holds true for type H varieties. Okay, now let's go back to the case B434. And in this case, the slope of f is 1/2. On the other hand, the slope of the tangent bundle is 6/14, which is smaller than 1/12. So the tangent bundle is unstable. And this is proof for the case of B434. And we can prove the main theorem by similar calculations. Okay, in the last minutes, let me give some remarks. Okay, so first, let me give one remark on the geometry of varieties in Pasquier's list. In his list, there are 7 types of varieties, H1 to H5, and P1 and P2. And the geometry of type H and the geometry of type P are very, very different. Varieties of type H are holospherical varieties, but type P are not holospherical varieties. And the group G, which is the identity component of the automorphism group, is not reductive for type H varieties, but they are semi-simple for type P varieties. And since this group G is not reductive for type H varieties, there are no Kähler-Einstein metrics on type H varieties. On the other hand, type P varieties are, how should I say, almost certainly Kähler-Einstein. Actually, I calculated the beta invariant for the exceptional divisor E over the closed orbit Z, and it is positive. So by using the G equivariant variative criterion of K stability, we can conclude that this X is K wholly stable. And so it is Kähler-Einstein. But okay, let me explain why I put here this question mark. Actually, the calculation of the beta invariant is very, very complicated. And actually, I use our computer program to calculate it, and it is very complicated. And since it is very, very, very complicated, I needed to check the calculation carefully. So I put here a question mark at the moment, but they are almost certainly Kähler-Einstein. Okay, now let me present the slopes of foliations, which is induced from the projection from the closed orbit. Then the slopes are as in this list. Okay, now I'd like to draw your attention to the sign of the slopes. In the first 5 cases, so for type H varieties, the slopes are positive. But for type P varieties, slopes are 0. So the foliations are Calabi-Yau foliations. And so, okay, so, and for type H varieties, they are not Kähler-Einstein, but type P varieties are Kähler-Einstein. So we can ask a very naive question, whether there is a relation between the positivity of slopes and the Kähler-Einstein matrix. And this is the first remark. Okay, finally, let me give one remark on the stability of tangent bundles. In previous sections, we have considered just semi-stability for simplicity, but depending on the context, it is also important to determine whether they are stable or not, and also whether they are polystable or not. And in general, stability of a vector bundle implies its polystability, and the polystability implies semi-stability. But if the bundle in question is the tangent bundle of a Fano manifold with Picard rank 1, then it is indecomposable. This is proved by Campana and Peternel. And since it is indecomposable, so the stability of the tangent bundle of a Fano manifold with Picard rank 1 is equivalent to its polystability. Okay, in the case of Pasquier's list, we can show, in fact, the tangent bundle is stable if it is semi-stable. Okay, let me give a sketch proof of this theorem, the stability of the tangent bundle in the case where the tangent bundle is semi-stable. And okay, as is mentioned, it is enough to show that the tangent bundle is polystable. And assume to the contrary that the tangent bundle is not polystable, then by considering the Jordan-Helder filtration of the tangent bundle, we can find the invariant polystable subsheaf F, whose slope is same as the slope of the tangent bundle. But since, okay, we assume that the tangent bundle is not polystable, so this F is a proper subsheaf of the tangent bundle. Then by the same argument of the proof of main theorem, we can show that this F defines a foliation, and which comes from the projection from the closed orbit. But the slope of this foliation F is, okay, is as in this slide. And in each case, the slope of F is different from the slope of the tangent bundle. So this contradicts to the fact this. So we are done. And okay, and this is the last slide of this talk, and there seems 4 or 5 minutes left, but I stop here. Thank you very much.
Thank you, Akihiro. Can you see the question on the chat?
Okay, I will. Okay, H2.
Oh, you want to? You want to explain it? Unmute yourself.
Oh, sorry, I couldn't understand the question. H235. What is H235? So okay, here we have this, and I see. Yes. I see. So the varieties of H2, H3, and H5 are not Kähler-Einstein, but since the tangent boundary is stable, so it is poly stable, and so it admits a Hermitian-Einstein matrix. So they are not Kähler-Einstein, but they are Hermitian-Einstein. Yes.
Any other questions? Okay. So let's yeah. Thanks a lot, Akihiro. So give him some applause again.
Thank you very much.
Thank you.